There, now it's gone. Well then, I'll spend the next few minutes here. So you didn't get on the camera the first 10 seconds.
Jeez.
Okay, problem number 1 is a function that you write. Problem number 2 is the first example of using your DH parameters to plot the configuration of a robot. You notice that in this case the alpha term is 0 all the way across. The reason for that is because we're dealing with a planar robot. That means the z-axis is pointing in the same direction on every one of those joints, and we're never moving out of that xy plane. Okay? So we will be setting our alpha value to 0, and then specifying the length and the angle that we're rotating about. So remember, this is our link twist, our link length, and our, let's see, this was our joint angle. Next one is when we start to actually get a little more involved. We still have a planar robot, but if you read the description, you learn something kind of interesting. This is not expressed in the xy plane. This is actually expressed in the xz plane. So you have to manipulate your DH parameters into, or so that you are rotating your z-axis first facing outwards from the page, and you can do that just by giving the initial joint angle a 90-degree rotation. And then everything thereafter will be set up the same as what we saw before. Notice that a few of these are worth 2 points. For that reason, as we go through, you'll only end up with 7 problems total instead, because 3 of them are worth 2 points each. Problem number 5 then is your first opportunity to start playing around with motion simulation. What you're going to do is you're going to take the example from problem 4, and you're going to use a for loop to change your theta 2 value from negative 30 degrees to positive 45 degrees. And what that'll do is it'll simulate motion, say, on that axis. You'll see everything in the past joint 2 stay in the same relative configuration, but as you rotate that joint, it will change the spatial orientation of those elements. The same thing as I had before, if you have not worked with for loops or any kind of loop control, I've provided a link for you so that you can look at the ins and outs of for loops. Later on we'll be using while loops a lot, and as we get there we'll talk about them a bit more. Problem number 6 actually takes us for the first time into 3 dimensions. Well, I shouldn't say for the first time, but for the first time in this assignment into 3 dimensions, and you can now see that we have both a twist angle and our theta angle. We only in fact have one twist angle associated with this. As you go through, you'll find out that that twist angle is associated with that hip axis. So what that's doing is it's allowing us to give a twist angle, or I'm sorry, a rotation about the z-axis on our base joint, and then we'll still have our up and down. These things are good for something. So still have your up and down tilt and so on and so forth on your subsequent joints. Good. And then finally we have a very similar problem to problem number 5. In this case though, we're going to go through and adjust theta 1 from 45 to 120 degrees. Then we're going to adjust theta 2 from 60 degrees down to 15 degrees. And then we're going to adjust theta 3 from negative 30 to positive 60 degrees. And finally theta 4 from 45 to 135. What you're going to do is you're going to express these motions in a different color. That way you can actually view the motion as it goes through. And just since I have it here, let me open it up and show you what this is going to look like. So this is where we're getting ready to go. I'll do that again. I wish I could run this full screen. So what you can see is that in this case, I'm starting off by adjusting that theta 1 angle, so I'm moving it whatever I just said. What was it, from 60 to 120 degrees? And then from there, I'm adjusting joint 2 along the path that it's supposed to follow, joint 3 along the path that it's supposed to follow, and then finally joint 4. And this is intended to show you the path that each transformation takes as it moves in space. Okay. Now, since our code is slightly more efficient than what the code was last time I taught this class, it's ultimately going to run a lot faster. As you saw in the function that I produced last time I taught this class, I went and had MATLAB perform a lot of operations that I did not need it to perform. In this case, we've streamlined it a lot, so even though I have the draw now function in there, it runs pretty fast, therefore it's kind of hard to see. That makes sense? Okay, so, and with that then, that brings you to the end of the assignment. So, any questions there? I got really ghetto in my programming technique on problem number 7. In fact, what I did was I took the entire code from problem 6, put it in a for statement, and then copied the entire code again, put it in a second for statement to adjust the second joint, and then again for the third joint and fourth joint. So I was horribly sloppy in my programming, however, it still got the job done. Okay. This is not a programming class. I'm going to probably be somewhat critical if you are just horribly inefficient, but I'm not going to be assessing necessarily your efficiency in your programming skill or style. Good? Okay, so with that, let me switch back to here, and we'll get to the warm-up activity. And this warm-up, I'm not necessarily expecting you to be able to go through this and determine the DH parameters on a robot by yourself yet, but you should be there within the next couple days. So, spend a minute seeing if you can't remember what each of the parameters are and which parameter are we pretty much throwing out. Much is the case with that robot and this robot and the majority of other robots, we're going to pretty much throw out the link offset parameter because we're just going to say that we're dealing exclusively with revolute joints throughout this robot. Now you'll notice in one instance we have an opportunity for link offset, but in fact it would be a fixed link offset. And as we go through here, we'll take a look at that. So, real quick, let me see if I actually... But it's really, so. So what are the 3 parameters we're going to be identifying for each joint link pair?
The link twist.
Link twist.
The link length. And the joint angle.
And that is your alpha, the link length. That is our R. Remember the book calls it A, but that is just not a good idea. And then finally our joint angle. And that's our theta. So go through and spend a minute seeing if you can't identify each of these parameters for the 6 joints that are specified on the robot. You want me to zoom in a little bit? See if I can. How's that?
Good.
This is actually a Kuna manipulator. Wait, is it Kuna or Kuka? Let me see here real quick. There is a Kuna and a Kuka. I actually think it's a Kuka robot. I don't know who produces it. It sounds very Hawaiian though. But I doubt that it's actually Hawaiian. Well, I shouldn't say that, I don't know, but it just doesn't seem as if many robots are produced in Hawaii. I don't know why, but not very surfboard-like. Okay, so starting, or where should we start?
With just the base.
Yeah, just with the base and work on through here. So what we can do is, if we go through and start defining our parameter list here, find the edge of the paper, we can say that this parameter list is going to contain our link twist, our link lengths, and our joint angles, all as vectors.
You might move the paper over a little bit.
Yeah, maybe I should, huh? There you go. Not that it really matters since that's virtually illegible. Okay, so what is the link twist on our A1 joint? How does the frame attach itself to the base joint? I'm going to do this and probably get myself in trouble. I won't take the cap off, that's it. So we're going to already be oriented the way we expect it to be. Z is going to be pointing up, X is going to be radiating out, and then Y is just going to complete our 3D coordinate system, okay? So is there a joint twist angle or link twist angle? Remember, the link twist is what aligns the former Z with the new Z.
Right, so there should be.
So in this case, there is no link twist because we already have that Z-axis radiating through the center of motion on that joint. So we can say that in this first joint, A1, our link twist is 0, okay? So let me just go ahead and draw in the Z-axis here. So there's the Z-axis for us, and it's going to be really interesting. Okay, how are we going to go through and find the link length then? Well, what is the link length? So if you recall, the link length is the distance, it's the shortest distance between the Z-axis on the A1 joint to the Z-axis on the A2 joint. So in order to find that normal distance, geez, I wish I could take these down. You know what, I bet I could, but I'm not going to. Oh, so it turns out that me and the dogs did not have pizza this weekend. I went and got some ribeyes.
It's a little bit better.
Yeah, I'm kidding, so. They were happy dogs. Okay, so that length is going to represent, or be the minimum distance between the Z-axis on the A1 joint to the Z-axis on the A2 joint. So we can see that here this vector is perpendicular to A1 and perpendicular to A2. That makes sense? Okay, in this case, I state that that distance is 100 millimeters. Okay, when we get to our final example of this, you'll see that we have to identify it appropriately, because we have to first identify where our z-axes are, and then from there we can figure out which physical measurement to use. So in this case, we have a length of 100 millimeters, and finally our joint angle is variable. So we would just call that theta 1. Good. How about the next set of parameters? And what we'll do when we establish this vector is then we'll be pulling information out of that vector to send into our homogeneous transformation in order to perform the transformation for us. So this is essentially going to be our parameter matrix, and that parameter matrix will contain everything we use in order to describe the characteristics of the robot. Okay, so the first thing we need to do when we go on to joint 2 to describe it, is we have to go through and figure out what the link twist is from A1 to A2. And if we look at this, we are going from, let's see, we're rotating about X. So X would be here, so we are hanging out here, and we're rotating Z so that it's in line with the new Z. Okay, so we can see that we're rotating a positive 90 degrees. That makes sense? So we're rotating a positive 90 degrees in order to get A2, the z-axis on A2 aligned. I'm sorry, the z-axis on A1 to be aligned on A2. That makes sense? Okay. And now, how much offset do we have?
750.
Actually, I messed up, didn't I?
Should be the 100.
Yeah, it should be the 100. What should go here?
0.
0. Good. Why is that?
Because it's the I minus 1.
It's the I minus 1. So we're looking at the distance from A1 to A2, and the joint the joint twist from A1 to A2, and finally the theta 2 is the joint angle associated with A2. Good. Okay, now what? Going on up through here, we can say that that's the next z-axis, or the z-axis to the subsequent joint, and what's the rotation or the joint twist associated with that? There is none, because the axes are pointing in the same direction, right? So in this case, we can say that there is no joint twist on this axis. There is a offset. Let's see, is that right? Yep, going from A2 to A3. There's a 750 millimeter translation, so that becomes our length. And then finally, theta 3 will vary in order to provide that degree of motion, or that degree of freedom. Good. So go ahead and spend a few minutes filling out the rest of this. And I'm doing this intentionally because the next one's kind of tricky. as sad as this seems, I think my handwriting on the board is better than my handwriting here, so. So seriously, it was awesome because Fred Myers had these little tiny patio stakes like this on the day-old rack. So I went and bought like this, I mean, huge pack of these patio steaks, and every time I threw a steak on the barbecue for myself, I just tossed 4 of those on for the puppies too. And boy, they picked up that habit real quick. So what do you think? So the way the axis is defined, we have to interpret this direction as your positive z-axis because our twist is going around the joint in the positive direction, okay? So with that then, we could say that, well, from this axis to the next axis, which would look something like that, and that's not quite right, but it's pretty close. Where or which displacement vector are we going along? Now, notice something here. When we go through and look at going from joint A3 to A4, we're actually looking at that distance there, which is listed as 75 millimeters. So from here to here, 75 millimeters, that's about 3 inches. That seems about right, depending on the scale of this robot. I just made up these numbers. These aren't off of a data sheet or anything. So what's kind of the disconcerting aspect of this? Where's the rotation actually taking place? Right there. So give me one of 2 things that we could actually do here when defining this subsequent joint or link joint parameters. One of the things I was curious, or was going to do, but it would have messed up our previous arguments for disregarding the D parameter, is I was going to use that D parameter in order to provide this offset from here to here. But what's a trick that we can use in order to get the job done? Notice the rotation is about the axis here. So really we could just incorporate the offset from here to here in our subsequent link length. That makes sense? And by doing so, we're saving ourselves from having to introduce that 4th parameter into our setup of the DH parameters. That makes sense? Now we very easily could have done that, but if we had, then we would have had to be introducing the link offset variable in every one of these, and then we'd have an entire field of zeros with the exception of that 1 parameter. So it is something that we could do, but just in in order to keep our matrix as simple as possible, we'll just incorporate this 200 millimeters as the sum of our link offset here and our actual displacement to the subsequent link. That makes sense? So what we see then is that we have a twist angle of, again, 90 degrees. So we're sitting here, we need to, and actually that would be a negative 90 degrees, wouldn't it? So we have a twist angle of negative 90 degrees. We have our link length of 75 millimeters. That's the distance to take us from the perpendicular or the z-axis on A3 to the z-axis on A4. And then we have our theta 4. I'm trying to think about this. Maybe we will need to introduce that. The way I did this before. Okay, so let's see. We've got from here, we're on the, yeah, so unfortunately we will have to, well, let's see. So if we go from here, rotate, so that Z is facing up and then fold it down, then we could get the job done. And then that link definition would just have no twist associated, or it would have, its theta angle would be fixed. So what we will do then is we'll twist it up and then we'll lay it down so that we can account for this x offset from here to here. Okay, so we will actually have a 90-degree rotation there. This takes us from A3 to the origin of A4 with respect to this location. And since we need to measure the translation along x, this then will orientate our z. And let's see, so that's back and then up. Yeah, so that's right. That will orientate our z, our positive x, pointing in the direction we want it. And then on our subsequent axis, we will have another 90-degree shift in order to bring the z in line, and then to offset it by the 200 millimeters. And now we'll have our theta 4.
So in the third column or the fourth, you don't have to have that in relation to theta 3, like it's just 90 degrees,
Good.
It doesn't.
So the reason why we had to do that is because we're actually, in order to get this job done without the use of your offset parameters, you need to set up the point so that it's translated to here, and then provide the 200 millimeter offset along the x-axis to the next joint. So what we're doing then is rotating it up and orienting x in the proper direction, and then we're translating the x, the 200 millimeters that we're saying, to the subsequent joint. If we had incorporated the link offset like we, like the DH parameters call for, then we could have just provided that link offset, or I'm sorry, yeah, the link offset, and we would have been done with it. But in this case, since we're using 3 parameters instead of all 4, we need to go through and move it up, perform the rotations, and then translate it along the x-axis 200 millimeters, and then perform the subsequent rotation to bring the z-axis back in line. That makes sense? This is something we won't need to do or worry about when we get to our simulation, because ultimately when we build that simulation, we're going to predefine what our DH parameters are. And however the DH parameters are assigned, we'll just characterize our robot. That makes sense? In fact, if you look on the robot that we're using is similar in nature to what we have here, but we're going to go through and predefine those DH parameters ahead of time. I'm not going to expect you to go through and identify them yourself. That makes sense? This is just kind of give you an idea of how to identify the parameters. So, okay, once we get to our A4 joint, then we see that we have a revolute joint about X and or about Z, and then A5 is on the Z axis. So with that, then we need to rotate it 90 degrees again in order to realign the Z axes. In this case, the Z axis runs right through it like that, and we can see that there is a 90-degree angle. Let's see, and that would be a positive 90 degrees because we hit it with a negative 90 degrees to align it here. And then we would have the joint offset. In this case would be 0. This 25 here is between A5 and A6. The reason it's 0 is because it's actually coincident on the Z-axis. That makes sense. It's kind of intimidating, right? I mean, partly because we're electrical engineers, not mechanical, so looking at anything that represents a real thing is somewhat irritating to do. So you're probably sitting back there like, I do this all the time, so.
I haven't gotten very far in it yet.
No.
Gonna get there though.
So where are you at? I mean,
I've just taken, I've taken AutoCAD and I'm taking SolidWorks.
so you're like just in your first year or so?
Yeah.
Okay. Yeah, this would have been a really good class to take after your statics class. Yeah.
Mm.
Are those two Q4s at the bottom? Well, the 90 represents one of the Q4.
What's that?
Theta 4.
Yeah, in this case, what we're doing is we're rotating on this axis negative 90 degrees to orientate the Z upward, and then we're rotating around to bring the x-axis so that it's pointing in the proper direction. Once it's pointing in the correct direction, then we can translate the 200 that we need and reorientate the Z so that it's pointing through the joint. So we're pointing the Z up, twisting the X around, and then in the next line, we're moving along X and rotating back down. That makes sense? Okay, with that then, since we have a joint that's instant on the same axis, we see that there is no joint offset, length, and we have a link twist of 90 degrees just to move the x-axis through the joint again. And finally, our theta 5, and then going from theta 5 back to theta 6, we have to kind of do this situation again, where we have to, let's see, what do we need to? Rotate Z up and then fold Z down. So yeah, I think we'd have to rotate 90 on alpha, rotate 90 on X, and then perform a subsequent rotation to get that. Wait a second, no we wouldn't, because this is on the same axis as our previous Z, so we just have to go through and rotate it in the negative 90 degree with a offset of 0. And then we're done. And that would be the parameters that we would use for this particular robot. Now it's, fortunately for you, this isn't a test item, right? Because there are no tests in my classes that I teach in the summer, okay? But if we did have an exam, this would be a great thing to go through. Maybe not the entire robot, but a couple of the joints, just to see if you could identify these DH parameters in that robot. It does get kind of confusing, especially when you start looking at positive and negative rotations, just making sure that you keep the direction of rotation appropriate so that you can continue to use that right-hand rule as you wrap around each of the subsequent axes. And that's ultimately what I do whenever I'm working with this, is I just keep my right hand up there and I point my hand along the axis so that I'm twisting in the positive direction. In this case, we see that we're twisting in the positive direction here. That tells me that this is the positive z-axis, and that allows me to keep the orientation correct. Good. Kind of cumbersome though. I mean, if you were designing robots, this is probably something that you do all day long, but in our cases, we're just going to be setting up the parameter list for the particular robot that we model, and from there then we'll go through and use the same parameter list for as a class. So this is something we'll develop together. All right, so let's see. Slightly different configuration. Spend a few minutes seeing if you can't identify the parameter list for this robot. It's going to start off very similar, however, after the second joint, it's going to vary slightly. And notice here that we actually have an opportunity to introduce a length if we're so inclined. We could put the origin here rather than up here, depending on how low the manipulator reaches. If it reaches down to this plane, then we might want to have this be the XY plane that we're working on, okay? However, generally what you see is you assign the origin of the XYZ plane or XYZ space in the center of your base joint. And I suppose I'll shift that down just a bit. I do need to head out pretty much immediately after class. I'm doing some work for my landlord over the summer, and I need to get over there and meet up with him to get a list of to-dos. So if you have not turned in your assignment, just make sure that it is under my door or in my mailbox first thing in the morning, and it'll be accepted on time. However, do not come into my office at 10 o'clock and say, here's my assignment, because at that point I will be forced to consider it late. And for summer classes, you really don't want any late work. It's better to get a 7 out of 10 on something than a 5 out of 10. So. The reason why I'm actually making due dates for this assignment, as I'm not in my 301 class, is this is really not a class that you can work at your own pace on. It's one of those classes, you pretty much have to do the assignments as you proceed through the class, because if you get behind on it, I don't necessarily know if you could get caught back up, so. Okay, so while you're starting through here, I'm going to go through and just pencil in the z-axis on each of these and draw those common normals. Okay, so at least for the first couple joints, setting this guy up is considerably easier than the last problem. Are you going to want to go through and define this as your origin, or do you want to just define it in the center of your? Okay, so if you define it in the center, what we see then is that we have, what's our twist? It'd be 0 because we're rotating about the z-axis on that first joint. Okay, our link offset then, if we're defining the center of the joint as our origin, would be 0. If we defined some point down here near the floor as our offset or as our origin, then we would have a link length associated with this displacement. That makes sense. And then finally, we have our variable, which is our joint angle, theta 1, that's actually providing the degree of freedom for us. Then what? You will hear people actually talk about these generally, well, anymore you hear people talk about joint 1, joint 2, joint 3, and so on and so forth. So they just number the joints. But if you talk to anyone that's been in robotics for a while, they'll sometimes refer to this as the hip joint, shoulder joint, elbow, wrist, and so on and so forth. Okay. Notice one thing here. What is joint 1, 2, and 3 primarily responsible for? Well, joint 1, 2, 3, and we could probably say 4 as well. Actually, I'll just leave it as 1, 2, and 3. Joints 1, 2, and 3 are responsible for position. What are joints 4, 5, and 6 responsible for then?
Getting the manipulator in the right angle.
Orientation.
Yeah.
Okay, so we have 1, 2, and 3, which are almost always used for positioning of the end effector. 4, 5, and 6 are responsible for orientating that end effector, getting it into the right general location so that it can pick up. Oh, that joint's locked, so that it can pick up whatever piece of product or manipulate whatever object it's intending to manipulate. Okay. So with that then, we see that we have 0 and 0 and our theta 1 that provides our degree of freedom. What are we going to do going from joint 1 to joint 2? Or from the hip to the shoulder? Going to have a 90-degree rotation. How much offset, or what's the length between A1 and A2? Or joint 1 and joint 2?
6.
6, okay. So in this case, we can see that these aren't quite oriented so that joint 2 is incident on joint, or on the axis of joint 1. But it's really close. If we were to draw it, it would look something like this. And that's kind of poorly drawn, but you get the idea there. The 6 millimeters or 6 inches or whatever else is just representing the normal or the perpendicular line drawn from the axis on joint 2 to the axis on joint 1. And then we have our degree of freedom, which is theta 2. Next couple joints are nice because they are in fact, or they are in fact parallel to joint 2. Therefore, we can say that the twist on joint 3 is 0, and for that matter, on joint 4 is 0 as well. The length going from 2 to 3 is 18 and 24, respectively. This is kind of misleading, okay? Can anyone think of a reason why we might not want to have a longer joint further from the base?
Because it is not as durable.
Say again.
It's not as durable.
Say again.
It's not as durable.
Not as durable. What can you say about the size of the motor needed to move the first joint up and down?
Smaller than the size of the motor for the second one.
Yeah, well, it would technically have to be larger, but if we tried to mount a subsequent motor on the third joint up there, in order to handle that, the torque associated with that long length, it would be just that much more weight that the second joint would have to handle. So typically what you do is each of your successive joint, your link lengths are progressively shorter in order to allow you to scale the size of the motors accordingly. That makes sense? So this isn't very realistically. Typically, the reason why I selected 18 and 24 is just because of the way the drawing was drawn, just to make it look proportional to the drawing. But the fact is, typically you would have the first length, or the R3 length be the 24 inches or centimeters or whatever the case was, and the subsequent length then would be the 18, just to allow you to size the motors accordingly or appropriately. You want the motors to be decreasing in size as you go further out the chain. Good. Okay, and then of course we have theta, let's see, this was theta 2, this is theta 3, and this is theta 4. Okay, and then if we go through from here and look at theta 5, then we see that we're going to be rotating it back perpendicularly. Since we rotated it through a 90-degree rotation to point it to the side, we're going to reverse that by moving a negative 90 degrees to orientate it back perpendicularly.
So you can use like negative 90 at the beginning and do 90 again?
You could, just depending on which direction you're wanting to make your positive z-axis. Okay. In this case, it didn't specify what a positive rotation and what a negative rotation was. Therefore, we're kind of free to assign this whichever way we want. Okay. Typically what I do is when I'm assigning these z-axes, I always relate it back to what something would look like in the first quadrant. Okay, so I point a vector off in the first quadrant, or even better, just along the x to z plane. That way I can show elevation and everything else, and make sure that the joint orientations make sense to me in that quadrant. That makes sense? So with that then, now we're going to have a negative 90-degree joint angle to go from link 4 to link 5. And that just makes sure that this once again is your positive z as it relates to my base joint. Okay. Our offset there is 2, going from R4 to frame 4, or I'm sorry, joint 4 to joint 5. So we have a 2 offset, and then we have a theta angle of, that's variable. Finally, we're sitting with one of those really weird joints again, because now we have to have a static parameter list that first rotates it off to the side and then rotates x to point in the appropriate direction. And then we can rotate that x around to point it perpendicular, or I'm sorry, along the path that we're manipulating the object. So in this case, we're going to go through and say that we're going to rotate it on its side again. So rotate it by 90. We're not going to have any joint displacement because that will occur on the, I'm sorry, we're not going to have a length assigned because that will occur on our next translation. So we'll have a 0. And then we're going to rotate this by 90 to get the x-axis pointing in the direction we want it to go. So let's see, we're facing up, we rotated it 90 about x, so that's like this. Brought it down, so we would actually be wanting to rotate it a negative 90 degrees to turn it on its side. You guys agree with that? Or would it be positive? I do tend to get myself turned around on this, so we want to have it pointing up. We're twisting it about z by 90 degrees so that our y-axis is pointing straight ahead. Then we're rotating it, we're rotating it about x, so we're turning that axis on the side, and then we're rotating it so that our y-axis is pointing down the line. That way on the subsequent rotation, we can rotate it by 90 to point it out of the robot. So 90, 90, and 90. We'll go with it. How about that? As we go in and start playing with these configurations in MATLAB, it'll become very appropriate to us if we're pointing it in the right direction or not. That makes sense? Okay, and then finally we'll have a twist angle of 90 degrees to get that axis, z-axis pointing in the right direction, an offset of 2 centimeters or millimeters, or whatever, inches or whatever I define the units as, and then our theta 6, which will provide our final degree of freedom. I'm almost thinking that should be a negative 90, but I can't swear to it. Too many rotations going on, so.
So the second to last entry, what is that exactly? It's not just another link between two, because it doesn't.
What this does is it provides, so what we have to remember is that our DH parameters are independent of the y-axis. If we could rotate about the y-axis, then we could, we have our Z pointing up, our X pointing down, the length, we could just rotate about the Y-axis to point it out. But our DH parameters are not dependent on Y, they're dependent on X and Z. Therefore, what we have to do is rotate Z, rotate about Z so that Y is pointing forward, and then rotate about X so that we're pointing out. Okay? And then after we're pointing out, then we have to do the rotation again to get the final Z-axis pointing through the joint.
It just takes a little bit to get.
Oh, you're not kidding.
It's one of those things where you wish you had like a 3D model that
Well,
showed
when
what-
we start playing around with this, we'll actually be looking at what happens when we, tomorrow when we start writing the code for this, it'll become very apparent when we choose the wrong angles and stuff. Because then we'll have links that are pointing back into the chain rather than pointing out the way we intended it to be. That makes sense. Okay, now you'll notice that we have an R7 here too. Where did that come into play? It didn't.
Yeah.
What does that R7 represent?
This is the length past the rotation point.
Yeah, exactly. That's the length past the rotation point. So that would be the tool offset from the center of rotation on that joint out to the end of the tool that you're manipulating. So if you had, say, a welding torch, that would be the tip of the nozzle on that torch. And that would just be there so that you could provide, you know, the minimum safety clearance as you're moving that manipulator around. Make sense? Alrighty, so with that then, let's go ahead and start talking about, we'll save the final example for tomorrow for our warm-up, because we'll need to play around with it a bit more. So let's go ahead and say that we want to model a chain with the following parameters. And this is a planar robot. So we're going to say that our list of parameters each have no twist associated with them, have lengths of 0, 13, and 7, and joint angles 37 degrees, negative 84 degrees, and 40 degrees. And we have 20 minutes. So what do these three parameters tell us? So this is my plus X, this is my plus Y, and this is my plus Z. Okay? Move over just a little bit. What are we first doing? We're rotating 37 degrees about Z. So that means that we're rotating about Z 37 degrees to point the robot in that direction. Then what are we doing?
Moving 13 units.
Moving 13 units. That is the length. Well, it's facing a negative 84 degree angle. So from here, we're shooting down. Sorry, this is kind of messy. By an 84 degree angle. So we have a length of 84 degree, or a length of 13 inches or millimeters or whatever the unit of measure is at an 84 degree angle into the negative, or in the negative Z direction. And then finally, we're turning